So this talk will be held by Colin. He is a researcher at system security at the Northeastern University. He has a huge interest in security in mobile and embedded application. And as far as I can tell from the description, you are going to tell us about a new way to investigate on Android application running on the Dalvik virtual machine, right? Yeah, so thank you, Colin.
Yeah, thank you for the introduction, and good afternoon, everybody. So, yeah, this talk will be about dynamic instrumentation of Dalvik applications on Android or any other platform that runs the Dalvik VM. So, a little bit about me. I'm a postdoc at the Northeastern University in Boston. I do mobile phone stuff, a lot of different mobile phone stuff, as you can see. I'm also one of the authors of this fine book, which will hopefully be released next year in April. So, Android application security is pretty interesting for various reasons. Maybe you want to find vulnerabilities, analyze malware. Maybe you just want to reverse engineer an application to see what it's doing. And finally, want to maybe attack an application, attack the OS. And currently, people were just really disassembling Dalvik code, looking at the Smali output, or run an application in an emulator or a sandbox and look at the traces, the execution traces or network traces, or maybe do some static instrumentation, so adding some code to an application. But this talk is really about dynamic instrumentation. So at the runtime, during runtime, and we're not going to really look at bytecode, so you don't need to worry that you have to know about Dalvik bytecode or anything. It's a much cleaner, easier way to do instrumentation. Of course, I was not the only one who was investigating that. So the Cydia substrate framework for Android also has the same capabilities, but it's really super complex. And parts of the source code, as I know, are not available. And also there's the Xpost framework, but this is more designed for doing OS mods. And my framework is it's small, it's built for security, it's really easy to understand and to use, and it's really designed to integrate it into your own application. And of course, it's released in full source code. So right now, people are doing static instrumentation, so they would take an APK, unpack it, which is converting the manifest file back to plain text, and so on. Of course, there are nice tools for that. And then they would you would look at the disassembly of the DEX files, then you would modify or add your own code to the Smali code, and then repackage, compile, sign, and then you would install it, run it, and then you would hope it would work. Because maybe your patch code has some bugs, or there's some tiny self-integrity check, and then maybe you have to repeat and repeat this process in order to do some instrumentation. That's what people are used to do. So what is dynamic instrumentation? So it's really about changing and modifying applications during runtime. So it's basically a technique that allows you to add and remove code and hooks on the fly. The dynamic instrumentation has been around for a number of years, but this talk is really about Dalvik instrumentation. And you can do very simple instrumentation. You just hook library calls of standard libraries, and then you can really easily see already what an application is doing with the system. Of course, if you want to do application or target specific instrumentation, you still need to disassemble the target application to actually find the points you want to instrument and hook. What are some of the really basic advantages of doing dynamic instrumentation on Android? For the main advantage, or one of the main advantages is that you don't need to unpack, disassemble, modify, compile, repack. You don't have to do all this, so you save a lot of time. Also, you don't need to modify the target APK. So really simple integrity checks are still working. Or if you have maybe an application that is signed with higher privileges, like the platform signature, you cannot repackage that without modifying or killing that signature. But the thing is, of course, Android applications are written in Java and they run in a virtual machine. So instrumentation is a little bit different than when you instrument like a native binary code. Just a quick overview. So this is this Android platform picture, which everybody loves and hates. And we are going to look at only this part, which basically runs everything, like all the applications in the UI you see. So small yellow box is a virtual machine, and then you have those core libraries. This is more or less the interesting thing for us. So how does actually the Android runtime work, and how does an Android process look like? Of course, you have the virtual machine and the core libraries. And every application or any system process that executes Dalvik code looks like this. You have a process that links to like the standard libraries, libc, libz, libjpeg, and so on, and of course libdvm. That's the actual virtual machine. And then, of course, the process also contains the Dalvik class that it wants to execute. And really, every application, like if you install, I don't know, Facebook or something, that basically works like this. And also the system processes like Zygote or the system server, which execute the framework, they work in the same way. So let's start with looking at the instrumentation. So the basic idea really of the instrumentation is we convert a Dalvik method to a native method, more specific to a JNI, to a Java native interface call. This is how we get control of the execution. And from there we can call once we execute in the JNI call, we call back to the framework, and we can call the original function we just took. So we can just create a really easy inline hook. And the nice thing is, when our code executes in JNI, we are in the land of C, so all the Java protections like private, protected, and so on, they don't exist for us. So we can access anything in that VM, which is really, really handy if you want to do instrumentation. So I will give you a very, very brief overview of JNI. You really don't need to understand JNI to understand this talk, but if you want to write your own instruments later, you have to like look into JNI. So it's basically a standardized interface to call native code from Java. And you can almost write any code that you can write in Java in this JNI interface, but you have to do a lot of work. And the basic signature of a JNI call looks like this. You have a method name, you have a result, and you have the JNI environment. And then you have a bunch of parameters. So the JNI interface provides us with a bunch of functionalities like find class, which gives you like a reference to a class. We can create new objects and so on. It's a really, really simple interface. So the actual instrumentation, how does it work? The actual instrumentation is based on injecting a shared object. So on Linux, this is just like a .so file into the running process. And this shared object provides for some very basic native code. So this native code hooks into the DVM or talks to the DVM. It resolves a bunch of methods to like resolve classes. And it provides the functionality to hook methods and call original methods. So this is our basic process again, but this time we already added our own code. So how does the hooking actually work? First, we need to find the loaded classes or references to loaded classes and methods. We find methods, classes and methods by just their fully qualified class name, and the method by the name and the method signature. This is an example for like accessing the compare to method in the string class, and it takes as an argument a string and an integer. Depending on what kind of methods, if the method is a virtual method or a direct method, you have to use different calls. But this is in the library all abstracted for you. So and the main idea is you resolve a method, change some of its internal parameters to convert it back or to make it a native class. And the most important ones are those. You change the argument, the JNI argument info, so the JNI subsystem can parse the method arguments. And the most important one is the access flags. You just add OX 100, which defines this method to be a native method now. And then you have your piece of code, which is a replacement function. So this is the function to replace the compare to function. You see the native, the JNI environment, the reference to the object, and the parameter, the string object. And then every call after this, and then of course the use GNI bridge. That's basically, you give it a, so with this function, we find the method descriptor, which is like returned in this like met variable, and then we just tell the DVM, hey, this method, please use this native function, Dalvik function hook, in this case, to execute this compare to function. Very simple. We need to modify a few settings of this method. Most specific is the register size and the argument count. And depending on what kind of argument you pass to the method, you have to give it a number of arguments you want to pass, a register size. Sorry. This is pretty well documented in the VM, and for example, this method takes it has int size of 2 because it takes one object as a parameter, and of course it's not a static method, so it has also this value, or like an instance parameter. And then once your code executed, you want to of course call the original functionality in order to like not break the application. Of course, in some cases you might not want to call the original functionality, but this part then we already covered. And to do this, you basically have to look up the method and the class again, revert the parameters, so all the parameters like the register size you have to store, then you revert it, and then you just like use one of the JNI functionalities in this call int method, pass the arguments back, and you get the original function to execute. This sounds, of course, like very complicated and cumbersome. You don't want to like write this by hand for every method. So I created this like really nice, easy to use lib-dalvik hook library. And what you basically do, you say, okay, I want to set up a hook. You pass it the name of the class, the method name, the method signature, the size of the registers, and a function pointer, which is a function short hook. And then you just call hook, and that's it. From then on, this function will be used whenever this method in this class is being executed. And of course, we also have like a functionality to call the original function. So you just have to call this prepare call, use this call something method from the JNI interface. You get the result, and then you just like reinstall your hook. Since we're doing an inline hook, we always have to do this prepare call, post call structure. But in the end effect, you will have like 3 lines of code every time. And if you simply just want to unhook something, you just call the prepare statement, and in the library, I think I put in a macro which basically is unhook. So very, very easy to use. Okay, but how do we actually install a hook into the system or into an application? For this, I created this hijack tool, which is basically a port and some enhancements of a very simple Linux shared library injector. And the steps you have to do after you create your library, you push the library to a data local temp. If you want to also load additional DEX classes, which I'm going to tell you about in a few minutes, you also have to change the Stalvik cache directory to be worldwide writable. And then you also use the hijack tool, provides the PID of the target process and the full path to the library, and then you just run it, and that injects the library into the running process. And it really works for any Dalvik-based process on an Android system, so for your normal application, but also for Zygote and system servers. So you can do modifications deep down in the core framework on your running device. Yeah. So, but sometimes you want to instrument applications very early, maybe before startup, in order to like see really everything what the application is doing. And in order to do this, we actually have to instrument or trace a Zygote. And we have to do this because, can you actually read that? Probably not. Anyway, so Zygote is like the base VM process on the system. So every time you like start a new application, like hit some icon on the application launcher, the activity manager sends a message to Zygote, and Zygote like forks a new process, specializes to that by loading the specific classes, and then like you have a new process that like runs your application. And in order to hijack or inject your own code during that startup process, instead of tracing or instead of binding to the PID of the target process, which doesn't exist at that time, we just supply the PID of Zygote, give again the path to the library, and add the special string, which is the full class name of the application. That has to like match to the main activity that is launched. Which is very easy. So normally when you start the process for the first time, you can just like run PS and then you see the class name, or you have to look in the manifest file. And yeah, so you just run this command, then you can either manually press on the button to launch your target application, and before the actual application code is executed, the library is injected into the process, and you can start instrumenting. Yeah, so some special features. So you also actually for this you also have to add the -z switch, and then yeah, the S is really just the full class name. If you do stuff on like really old Android devices, you also have to add the -m switch to disable calling of mprotect, and then you can like get some more output from the hijack tool by just adding more debug level. So. Let's take a look at how actually the instrumentation code flow works. So we have some application and some method in it. If we like hook it, the application will go down and your hook will be executed. And yeah, your hook might or might not then go down and call the original function, and then apparently at some point return the execution back to the main application. So very, very simple. And if you just want to like look at what an application is doing, you can build like a very simple proxy, which is really, take the parameters, maybe log them, call the original function, and return. So with this technique, you can already do some lightweight monitoring and reversing. So maybe you have an application which is like somehow obfuscated. Maybe there is like some string encryption, or maybe some reflection to do more obfuscation. And so I created a small tool or a small demo library which is called String Monitor, where I just hook into various string classes like string buffer, toString, comparison. Functions are always interesting because applications might use it. That's like control flow changing operations. That's like the interesting points in the application. And then there are a bunch of string classes, and then of course like get method, which is like used in part of reflection, so you can see actually what methods are being used. Very, very simple demo. Yeah, I have something later on that too. You can just continue, and if you say, hey, if you don't call the original code, you can also do some other stuff. And one very interesting thing for me was just disable digital signature verification. And this is like really used for all kinds of different things. And this is like a really, really easy hack. You can just take this Java signature verify method, overwrite it, replace it with this like 1 line, 2 line of C code, which just returns 1. And if you load it into the application, that application will think all the signature it's going to check are valid. And yeah, you can do amazing things already with that capability. So these are where like these two things where you just like either monitor stuff or like really disable some checks. It's like that's only the beginning. If you want to do more sophisticated instrumentation stuff, you already, of course, want to like write more code. And writing all this like code that interacts with Android application in the Android framework, you really want to do that in Java, and don't want to like write everything in C, G, and I. So I added small functionality, which just like loads an additional class into the process. And actually all this functionality again was available in the DVM, and just like added like some nice wrappers around it. So what you basically can do, you can just write your Android code in Java, compile it with like even just like Eclipse, and then you can just like take your classes.dex file, throw it onto the device, and then you can just load it. You have to like just give it the dex file, and of course tell the DVM which class to load from that dex file. And when we want to load additional classes, the flow of the application or the flow of the instrumentation looks like that. In the first step, we have the benign process. In the second step, we load our native code, which then like calls to the DVM and can hook stuff. And this code can also load a class and call methods of this class. So the lower side, we have like our own classes, which has our like instrumentation code in it. And the loaded classes can just be used like any other class. They also can load additional things. The only like complication so far, if you want to use inner classes in your instrumentation class, you have to define and like add 1 line of class loading for each of those inner classes. One thing to load additional classes, you have to make the starter Dalvik cache directly writable. And in order to update your Dalvik code, you have to, or your injected Dalvik code, you have to delete the cached version from this directory at each time. So while you're developing your instrumentation, you have to always make sure to really delete this file, because otherwise you will only be loading your old version. And with this, we come to the instrumentation code flow version 2. So from the hook, we now can load an application, load a class into our application or like into our target process, and then call methods which are like written in Java that perform instrumentation or a utility for your instrumentation. So now we have code that's running inside the target application, either native code or Java code, but we really want to interact with the target application and, of course, the Android framework. But in order to access or to interact with the application, you really need access to the application's objects, so to the class instances. And there are a couple of methods you can use for that, for example, like methods or parameter scraping. So you can just hook a method in the process that gets, like, for example, a context parameter passed in, like Android content context, and then we can just take the instance or the pointer to that class instance and pass it along to our instrumentation framework, which then can, for example, send intents in the system and so on. Yeah, what else? Yeah, you can also access fields. So what you, if you know like the name of a field or like a class field, you can just like find the class, get the field ID, and then just read it. Also very simple. Yeah, and there is like more stuff you can do. You can also, if you like only have access to an inner class, you can easily get a pointer or a reference to the outer class, which is like this generated variable. This is this value $0, which just like points to the outer class. Just multiple methods to like get pointers to the class. Yeah. But yeah, there's if you don't like need to have like very specific ways to, or if your code basically runs in a UI thread, you can also just like use this activity thread, and you can just like get from this activity thread, you can just like get a pointer to an application context very easily. So it really depends on where you instrument, how your instrumentation code looks, if you're running in the right thread, and so on. So what did we do with this so far? For like a paper earlier this year, we wanted to change the local SMS routing on an Android phone, and for the paper we like took the Android source code and modified it and then compiled it. And of course it's like very tedious, and you don't want to like do this all the time. So at a later point, I just took my framework and re-implemented that, and we hooked this COM Android internal telephony, the SMS dispatcher. So this is the method that is called when every time an SMS comes into your system. And the nice part is with this instrumentation, you can just instead of recompiling everything, you build your instrumentation framework, you can save a lot of time, and you can build your tool or your instrumentation library once, and then deploy it on like 5 different Android devices, which maybe run based on different source. So it's really a huge time saver, even for like stuff that's not directly security related. If you just want to like prototype software, prototype OS extensions, and so on. Yeah, and whenever you like dig around other applications and maybe want to look at classes, like what are the methods, what are the method parameters, what are the internal values, variables, and so on, you can use like some functionality from the DVM, this class dumping, and just like say, hey, what's actually inside this class? And again, I just for an example, I just use the string class. You can see all the different methods. Of course, I retracted something just because the slide is very big. So you can very easily look inside how the classes are looking like. And then from this, you can very easily just like copy paste the parameter list or the signature into your instrumentation code. Yeah. So now we know how to modify applications. But can we also modify stuff globally? And of course we can modify stuff globally if we just inject our modification into the Zygote process. This modification gets distributed to every application that is started or forked off from Zygote after we added the instrumentation. We can also inject stuff into the system server, which like runs part of the framework. So if you want to do a modification deep down in the framework, you just push your instrumentation into the system server. So one thing you can do is like, hey, let's disable signature checking on the device globally. Then you can just like do inject like our verifier that always returns 1 into Zygote, and then like basically signature verification is like gone everywhere in the whole system until you, of course, reboot. But there are like many other applications where you like want to do like global instrumentation. Okay, so I showed you like some very basic stuff, but of course you're not here to only like say like, hey, we can like print out what string functions are called. So for a proof of concept, we built a nice little attack, and let's look into that. So I guess everybody who has like an Android device knows about this in-application billing. You can not only buy applications, but you can also download free applications. In the application, you can just like buy like coins or like remove the ads or convert it to a full version. And yeah, Google takes their 30%, and they say, oh yeah, we make a lot of money of it, so a lot of people apparently use it. And if you look at this, it's like, yeah, this is quite some money you can spend on just like buying some coins in a stupid game. So how does this thing actually work? So you have your own application on the left, and then you have the Android market. And there's basically just like an IPC mechanism where you can like request billing, and then like Google will take a request, send it to the backend server, sign it, send it back to you, and then the application says, oh, yeah, the user paid. Now you get like your thing in the application. And then you have a bunch of extra stuff. Some applications like will use like a backend server, and they actually should use a backend server, as you will see in a second. So the goal was, hey, can we trick this payment thing, the payment, to actually get free content, unlock full versions, get some coins. And of course, people have done that. People have modified the application, for example, to like just skip the payment and just give you whatever like you're selecting in the buy screen. Or you can very invasively like modify the market application, but this breaks a lot. And of course, every time something updates, all the stuff has to be redone. And you really don't want to like screw with the market application of your device. So what do we use? Of course, we use our dynamic instrumentation tool. And the nice thing, you can build this attack which you can start and stop on demand. So if you say, okay, I want to play this game, I want to get some coins, you just like start it, play the game, and then afterwards we can like really stop it. And the nice thing is we never actually have to look at how an application works. The attack is completely transparent towards the application. So if the application is updated, we don't even care. Of course, if like there's really, really specific changes in the market API, of course, then you have to adapt. But really the key point is, you don't have to touch individual applications to attack them. You install your tool, and everything that uses that API is owned. So now we're coming back to the signature verification. So because normally after something is bought, you get some information which is signed by Google. And in your application, you check, hey, is this thing is a signature good? And if it's good, you say, okay, this item is bought. Here you can have it. Of course, we can just override that, and then the signature part is gone. And then we just have to instrument some API here, which is basically only one call. So instrument this one call in this application, or in the market application, and bing, you get free stuff. And everybody likes a good demo, but I only have a video. So it's only 4 minutes. So let's start this application first. For the ones who don't know how the payment works, just a quick run through to the payment. I guess everybody knows this game. So let's get some stuff. So of course we want to buy something. And you see, okay, buy this. And says, okay, would be $5 normally, so okay, let's not buy it. And as you can see, you can also pay not only via credit card, but also via your phone bill. Yeah, so there are like a lot of different nice payment options. Yeah. It's just like to show a bunch of games and how much they charge. $30. Yeah. So, okay, let's start our tool. Of course, for all the instrumentation stuff, you need to have like root on your device. Yeah, this is a very old version, so it has there's still some shell scripts involved. So now let's go back to the game and see what's happening. Let's try the expensive one, since it's probably free now. $20. Now we go back, and you see, oops. Because it's so nice, let's just try also the cheap one, and there you go. More coins added. Okay. Let's buy something here. Okay, so far this was like pre-installed applications, so I could have like modified something. So I will download something directly from the market, and right from the market screen we can start the application. You will see it's also applying there. So we don't really, there's no like reverse engineering modifying of the applications. Let's go to the market. Let's install this thing. Let's see if we can. Okay. The screen will flip because of the specific game. It's like not the perfect choice, but so let's get some coins. You can see. Let's go back. You have to go back multiple times because you need to get back to the game. And cha-ching. Yeah. So, freshly installed from the market. And I'm already almost at the end. So dynamic instrumentation of Android, of the Android runtime, really allows to modify applications in the framework in memory. You don't break any signatures. It's really, your instrumentation tools are really portable across devices. The GNI trick is actually super stable because it's not a hack. That's just like how the GNI interface on Android works. So far we can only replace complete functions, so we don't modify bytecode yet. Actually, I'm working on this a little bit as a side project. Yeah, and I think you should be able to steer up the whole Android application security scene a little bit, because all the obfuscation and the use of reflection is kind of useless. because during runtime, everything is there at the time you want to use it, and if you can just like hook in, you can see and modify all the stuff. Yeah, at our lab, we have various projects where like students are like using that to like do other interesting things. So there should be some more upcoming fun things. And of course, the whole framework is open source and released. You can just like go to my GitHub page and download everything. Yeah, including the injection tools, examples for the string monitoring, for hooking the SMS dispatcher, but of course no source for this Google Play attack, because we don't want to take away like the money from all the developers who like spend hours to like write software. This is like purely to show like the powerful possibilities you have with this framework. And also we use the framework to like do good stuff. So we wrote a third-party patching framework for Android. So if you have an old device and you don't get updates anymore, no security patches, you can install our patches, and we have like a demo version on rekey.io. If anybody remembers like this master key series of bugs, yeah, there's a patch of that for that you can directly install. And I am through. I would thank you everybody for listening. I think we have time for questions, do we?
Let's go. A question for microphone number 4, sorry.
Colin, here. Have you checked your software against sorry, antivirus software?
No, not yet.
Okay.
You mean like instrumenting antivirus software, or?
Well, no. Well, antivirus software claims that your software is not good software.
We haven't released any of the instrumentation tools directly, so that's just really, the tools is like really for you yourself to like build tools and then distribute them. I don't have like a tool like in the store which I can check against it.
Okay.
So.
Yeah, number 1.
So recently there has this Android runtime been introduced, which is, as I understood it, they compile the stuff now to a more low-level code and execute it natively. Yeah, do you have any research in the RT, in the Android runtime, which is now rolling out, or is it really only Dalvik VM? So, because you only talked about Dalvik now, and I guess ART is the future, so what about
So I haven't looked into the ART stuff yet, but ART basically just is ahead of time compilation, so they compile the Dalvik code to native code. I think last year I did a talk about like how to instrument native code on Android, so you could use that. But if you just like want to get stuff out of like some application, you can still just change between Dalvik and ART. And as a resource vehicle, which this like tools mostly are, you can just like not switch to ART for now and use that. But yeah, I haven't looked into ART at all, but a good point.
Thanks.
Thanks, Colin, for the nice talk. Is there any difference between hooking some custom code to a normal app or and a background service or something?
Oh no. So you can just hook any, like if there's a service, if a service is running in its own process or like inside another process, you can hook everything. So we hook the system framework, so just like system_server process, or yeah, you basically can. So far, we didn't have any problems to hook something. Sometimes you really have to be careful with like threading, of course, because if your code executes in the wrong thread, yeah, you will crash it probably. But so far, we could like in place hooks like everywhere. Especially like the string monitoring stuff is very simple, and you can just like really just like install it in any or inject it into any application and.
I have one more question. When you want to hook something system-wide, you need to hook it on a Zigoti process. So is there any self-check in the Zigoti process that it has some changed execution flow or something in it or not?
Oh, so far there's nothing like that. Of course, if you have like one of the like newer devices with like SE Linux and everything, you have to switch off a lot of like system security settings in order to like use the instrumentation or to even like run code with root privileges. But my code works under the prefix that you rooted your device and have full control. Because of course, if the system prevents you from working with other processes, and the library injection works via ptrace, so if ptrace is disabled, of course, you cannot do the injection.
So will your code work on Android KitKat 4.4 because it's a bit hard to get a root?
Yeah, of course, it should work on any device that runs Dalvik when you have root privileges. So I'm not like really in the business of like rooting phones. There are like a lot of other people which like have made that their primary hobby, but it's not mine.
Thank you.
There is also a question from the Signal Angel, I see.
Yeah, regarding the backend server for the in-app payment, there is the question, what are the pros and cons to use one?
So if you don't use a backend for your own application for payment, then your application can be with like an attack similar to ours. You can like get everything for free. Basically, what you have to do, you have to take the signature or the signed data you get from the Play Store application and send that to your backend server, do the signature verification there, and send the answer back. Because now you could also still modify the application to check, to like disable the signature or the response, to like fake a positive response from the server. But for that you have to like disassemble the application, understand how the application works, and that's way more work. So without a backend server, without doing the signature check off device, you really make yourself very vulnerable to attacks like that.
Yeah, so I think that's pretty much it. Thank you very much, Colin.